Welcome! This video will guide you through an introduction to link maps. Link maps are graphical representations similar to concept maps or knowledge maps. However, link maps are designed specifically for physics. This video presentation will take you through an introduction to the idea of link maps and will also apply a link map to a topic in motors and generators. To start off, we need to talk about what link maps are. Link maps are a graphical representation of physics knowledge. The links within the maps represent the connections between various bits of physics knowledge. As such, an integral part of link maps is understanding the structure that represents the ideas. We will now briefly go over what the various shapes and colors mean in the context of link maps. Firstly, this blue box represents a directly related concept. This yellow box signifies a relevant and important equation. This orange color signifies a vital law, idea, or concept. Real-world practical applications or examples are shown in green underlined text in a black box. Finally, related physics knowledge is shown in a cloud. We will now go over an example of map structure. The example we'll be looking at is the example of a common cold. Two directly related concepts to the common cold are the immune system and the cold virus, here shown in blue text. Because they represent vital laws and ideas, they are in orange. A related piece of knowledge to the cold virus is germ theory, so it's shown in a cloud. An equation which can help describe germ theory is given here. Because it's an equation, it is shown in a yellow box. Now, germ theory informs the development of medicines, which is a real-world application. So it is shown here in green underlined text in a black box. Now if we look back over here, we note that the immune system actually attacks the cold virus. This leads to the symptoms of the common cold. Since these symptoms are real-world examples, they are also given in green underlined text in black boxes. The first symptom shown here is a fever. The second symptom is a sore throat. And a final symptom could be a runny nose. Now, medicines are linked to these symptoms because they often offer a treatment. As you can see, this link map shows how the various bits of knowledge related to the common cold fit together. This example has introduced you to what link maps are all about. You will now have the opportunity to put your own link map together. You will receive various parts of a link map on the motor effect. In groups, try to put a link map together. You will have about 5 minutes to do this. Okay, let's have a look at what a link map on the motor effect should look like. First of all, the motor effect is when a current carrying conductor in a magnetic field experiences a force. So, it is a central concept linked to the motor effect. Now, the direction of the motor effect force is given by the right-hand palm rule or the right-hand push rule. The rule states that using your right hand, if you align your fingers to the direction of the magnetic field and your thumb to the direction of the current or the positive charge movement, your palm will face in the direction of the force. Therefore, the right-hand palm rule or the right-hand push rule is linked to the motor effect via an arrow which states that it is related because it describes the direction of the motor effect force. Now, this equation represents the magnitude of the motor effect. The F is the force of the motor effect, B represents the strength of the magnetic field, I represents the strength of the current in the magnetic field, L represents the length of the conductor in the magnetic field, and theta is the angle between the length of the conductor and the magnetic field. Because it represents the magnitude of the motor effect force, it is linked to the motor effect by an arrow which shows that it is related through the magnitude of force. A related physics idea is the concept of torque. Now, torque is defined as the tendency for a force to rotate an object. On the link map, it is shown as a related concept to the left here. The equation for torque is given in this yellow box, and it is that torque, tau, is equal to the force applied times the perpendicular distance to which that force is applied. Therefore, it is related to this cloud here. Now, the torque on a current carrying coil in a magnetic field is equal to this equation, where tau represents the torque on the coil, n, the number of turns in the coil, b, the strength of the magnetic field which the coil is in, I, the current in the coil, a, the area of the coil, and theta, the angle between the plane of the coil and the plane of the magnetic field. Now, this equation comes from both the torque equation and the force equation for the motor effect. So it is linked to both of these equations and shown here. Now, if we take that equation for the torque on a coil in a magnetic field, we can see that to obtain a torque going in a constant direction, the current inside or through the coil has to be reversed every half cycle. This is accomplished using a split ring commutator. The use of a split ring commutator has a real-world application in DC motors, as you can see here. Therefore, the real-world application of DC motors is linked through here. Again, going from the torque on a current carrying coil in a magnetic field, we can see that the torque on that coil is proportional to the current. This will allow us to make current measurements by examining the amount of torque. The practical application which this is used in is in galvanometers. Within galvanometers, the torque on a current carrying coil in a magnetic field leads to a reading being read out on a scale. This reading will be proportional to the amount of current going through the coil. So, galvanometers, by looking at that torque, can measure the current going in through the coil. Therefore, the application of galvanometers is linked through here. Finally, if we think about the motor effect force, if we use an alternating current, that current will produce a back and forth force on the coil. The practical application that uses this is the loudspeaker, in which an AC current is passed through a coil, which leads to a back and forth force on the coil, which in turn produces sound. Therefore, the real-world application of loudspeakers is linked to the motor effect through there. You will now have an opportunity to make revisions to the link maps that you composed earlier. That's all from me. I hope you have gained an insight into link maps from this short introduction.